All right, so we're going to start chapter 3 now. The first thing that I want to discuss is the multiplication rule for counting, or it is also known as the principle of counting. Okay. But before I tell you what the principle or the rule is, I want to give you a motivational example. So let's consider 3 locations, and the locations are labeled as A, B, and C. And suppose that there are 3 paths from location A to B, and there are 4 paths from location B to C. Okay? The question then is, how many possible paths are there from A to C? How many possible paths are there from A to C? Is the question clear? Well, let's visualize this. So I have location A, B, and C. So from A to B, I have 3 paths. From B to C, I have 4 paths. Right? What's the total number of paths from A to C? I'm sorry? What's the total number of paths from A to C? Say it again? Yeah. You can just count it, right? What you want to think, the way you want to think about it though is, for each path from A to B, there are 4 possible paths from B to C. Right? For each path from A to B, there are 4 paths from B to C. So think of this. Think of your first task is to go from A to B. So the first task that you have for each way of completing the task, the first task, there are 4 ways of completing the second task. Okay. So because there are 3 ways you can go from A to B, and for each way to go from A to B, you have 4 ways to go from B to C. So the total number of ways to go from A to C would be 3 times 4. Okay. So the answer here is the total number of paths from A to C is 3 times 4, which is 12. Is that making sense to you? For every path from A to B, there are 4 possible paths from B to C. So the answer is 3 times 4. Okay, so let's generalize that. Suppose that I have A, B, and C. Now I have n paths from A to B and n paths from B to C, right? Once again, for each path from A to B, there are n possible paths from B to C. So therefore, the total number of paths from A to C will be what? But together there are how many paths? Yeah. So together there are mn paths from A to C. That's pretty much the multiplication rule, but I'm going to state that in a little bit differently in a bit. Any questions on that? So this is just to help you visualize the multiplication rule. So let's look at the multiplication rule, or also known as the basic principle of counting. Suppose that we have two experiments. One of them is denoted by exp1, the other one is denoted by exp2. Suppose that these two experiments are to be performed, and suppose that experiment 1 may result in any one of m possible outcomes. Okay, and for each outcome of experiment 1, experiment 2 has n possible outcomes. Is everybody clear? What is an experiment? For now, just think of an experiment as just something that has outcomes. Okay? And an experiment is just something that has outcomes. The question is, how many ways can we perform the two experiments? Okay. So what is the total number of outcomes of the two experiments? Well, the total number of outcomes for the two experiments is m times n. Is that making sense? Experiment 1 results in m possible outcomes, and for each outcome of experiment 1, experiment 2 has n possible outcomes. So together there are mn possible outcomes of the two experiments. Well, how do you prove this? Well, pretty simple. Basically what we are counting here is that the total number of pairs of outcomes of the two experiments. So the proof is pretty simple. Let A1, A2, AM be the outcomes of experiment 1, and B1, B2, Bn be the outcomes of the second experiment. Okay. So what are the I'm just going to list out the possible outcomes of the two experiments together. That is, list out all possible pairs of outcomes of the two experiments. Am I making sense? List out the total number of pairs of outcomes of the two experiments. And if you do that, you basically get a table. So the first row is the outcomes of experiment 2. The first column is the outcomes of the experiment 1, and then within the table I wrote down all possible pairs of outcomes, right? All possible pairs of outcomes. Is that obvious that I have m times n entries in the table? Is everybody clear on that? I have m times n entries in the table. Any questions on that? So that shows that the two experiments have mn possible outcomes. Okay, so here is an example. Do we have time? Yes. A small community consists of 10 cloned women, each of whom has 3 cloned children. Okay. I was trying to get some pictures from the internet, and then initially I thought I'm going to use a different picture for each person, but then I was like, well, that's going to be too much work, so I'm just going to use the same person for all the 10 women. Okay, so if one woman, spelling error there, but okay. If one woman and one of her child are to be chosen as mother and child of the year, then how many different choices are possible? Now, all the problems that we're going to look at are called counting problems, okay? And some of them are easy, but some of them are really brain teasing, okay? So once you know the answer, it's pretty easy, but they could be a little bit brain teasing problems. Okay, so how do I answer that? First of all, are you guys done writing it down? Everybody's done writing it down. Okay, so we have 10 women with each one has 3 children, right? So the question is, we are picking one woman and a child of her to be the mother and child of the year, right? Mother and child of the year. And how many different choices are possible? I'm sorry? Okay, how are you getting that number? Yeah. So the way you want to, in terms of the way I stated the counting principle, just think about experiment 1 here. Experiment 1 is pick one woman. Spelling error. Okay, and so here the number of possibilities is what? And let me write down experiment 2. Pick a child. So I can pick a woman how many ways? Well, there are 10 women, right? So there are 10 possible ways. There are 10 possible outcomes for experiment 1. Okay, once I choose a woman, then I pick a child, and how many ways can I pick a child, or what's the number of outcomes of experiment 2? Well, that's 3, because each woman has 3 children, right? So the total number of outcomes of the 2 experiments then is what? 3 times 10, which is 30. Is everybody okay? And pretty much, if you visualize, pretty much you have a woman with, so if you think of the outcome, 30 outcomes in terms of pairs of mother and child, right? So, for each family, I have 3 possible pairs, right? For each mother, there are 3 possible child, right? So, if I am pairing up a mother with a child, right? So for each family, I have 3 possible pairs, and there are 10 families, so there are 30 pairs possible. Yeah. Yeah. Any questions on that problem? Easy enough? All right. All right, the general basic principle of counting. The general basic principle of counting is that instead of having just 2 experiments, what if we have k experiments? So suppose that we have k experiments and they are denoted by exp1, exp2, expk. So assume that exp1 may result in n1 possible outcomes, and for each possible spelling error again, for each possible outcome of experiment 1, there are n2 possible outcomes from experiment 2. Inductively, for each possible set of outcomes of the first j experiments, there are nj plus 1 possible outcomes of experiment j plus 1. Then there are n1 times n2 times nk possible outcomes of the k experiments. Okay, go ahead and write it down and let me know if you're done. So this is just having more than 2 experiments. Okay. Now, by the way, these counting problems that we are doing now, they will be very, very important later on when we try to answer probability questions. Okay. Okay, so let me read this one more time. So we have k experiments, exp1, exp2, expk. exp1 may result in n1 possible outcomes, and for each possible outcome of exp1, there are n2 possible outcomes from exp2. And inductively, for each possible set of outcomes of the first j experiments, there are nj plus 1 possible outcomes of the j plus first experiment. So then there are n1 times n2 times nk possible outcomes of the k experiments. Everybody understands this statement? All right, so here's an example. A college planning committee consists of 3 freshmen, 4 sophomores, 5 juniors, and 2 seniors. A subcommittee of 4 consisting of 1 person from each class is to be chosen. Then how many different subcommittees are possible? How many different subcommittees are possible? 12, 10, 40. What is that? 8? Anybody? How are you getting 120? Multiplying what? Okay, and why can you do that? And so on. Okay, so the way you can think of it is the following. We can say that experiment 1. So remember, in order to make a subcommittee, you need a student from each class, right? And so experiment 1, let's say you are pick a freshman. And then you can say that experiment 2 is pick a sophomore. Experiment 3 is pick a junior, and 4 is pick a senior. Okay. And so experiment 1 can be done how many ways? Well, there are how many freshmen? There are 3 freshmen. There are 4 sophomores, 5 juniors, and 2 seniors, right? So the experiment 1 has 3 possible outcomes. Experiment 2 has 4 possible outcomes, and so on. So by the principle of counting, then our answer would be 3 times 4 times 5 times 2, which is exactly 120. Are we okay with that? Easy? Okay. Whoops. Okay, one last problem. How many different 7-place license plates are possible? How many different 7-place license plates are possible if the first 3 places are to be occupied by letters and the final 4 by digits? And I was looking for license plates, and fortunately I found one with exactly what I needed. Okay. Okay, what's the answer?
17 million.
All right. Let's just say it in terms of the factors.
26 to
Okay, yeah. So the way you want to think about it, you have 7 places, right? So you have for the first place, the second place, the third place, 4th, 5th, 6th, and 7th. Okay? Now, the first 3 places are to be occupied by letters, right? So how many possibilities do I have for the first place? Well, assuming that we are using the English alphabet, we have 26 letters. So there are 26 possibilities for the first place. There is no restriction on whether I can use the same letter or not, so there is still 26 possibilities for the second place, 26 possibilities for the third place, right? Now the last 4 are digits. We have 10 digits, right? Unless we are from ancient Babylonians, right? They use 60 digits, right? So 10 digits. So 10 digits would be, I have 10 possibilities for the 4th, 10 possibilities for the, what is that, 5th, 10 possibilities for the 6th, 10 possibilities for the, and if you just multiply all of them, whatever you get, that's the answer. Okay, so you're going to multiply all of them. Now, what if there is a restriction that you cannot repeat a letter or a digit? 10, 9, 8, 7, yeah. Everybody gets that? Okay.